Okay, we'll now do the section 5.3 in probability. This one deals with conditional probabilities and independence. And so what a conditional probability is, it's the probability of one event given another. So it is the probability that one event will occur given that another event has occurred. So, for instance, let's say event A is that I'm going to go golfing this afternoon, and which ordinarily, let's say on a Saturday, that's the probability of that is probably about 80%, I would say, in general. Event B is that it rains, okay, whether or not it's going to rain. And so if event B occurs, the probability of A is going to go way down. And so that is what we would call a conditional probability. And so the notation we have for that is this. That would be the probability that A occurs given that B occurs. Or it could be, let's say this. Let's say event A is that you get dealt a king. So dealt a king on the first card dealt to you from a 52-card deck. And let's say that event B is that you get dealt a king on the second card that you get dealt. Well, these events certainly aren't what we're going to call independent. And so we may want to know, what's the probability of that B is going to occur given that A has occurred? In other words, what's the probability that you're going to get dealt a king on the second card given that you've already been dealt a king in the first card? Well, if we want to calculate that probability, we would say, well, if we've already been dealt a king in the first card, first of all, there's only 51 cards left in the deck if we're assuming that we're not using replacement, which in general we don't. All right? And so then you say, well, how many kings are there left? There's 3. And so that is the conditional probability that B has occurred given that A has occurred. Now, we may also say, well, what if you did not get dealt a king in the first card? That would be the probability of B given A complement, given A did not occur. So this is saying on the first card, you did not get dealt a king. And so what's the probability that you're now going to get dealt a king on the second card? Well, there's still 4 kings left in the deck. And so that would be 4 out of 51. So those are examples of conditional probabilities, the probability of one thing given another thing has occurred. And conditional probabilities allow us to show independence. So independent events just means the occurrence of one event in no way influences the occurrence of the other. So independence means the occurrence of one event is not associated with a change in the probability of another event. And so we would say those events are independent. So for instance, like let's say if we roll this die and if we flip this coin. Okay, we roll the die and flip the coin. They're independent events. Whatever occurs here has no influence on whatever's happening here. So if event A is that you roll, let's say, a 5 or a 6, and let's say event B is that you flip a coin and get heads, they don't influence each other. The flipping a coin and getting heads is always 1/2, regardless of what happens with the die. And the die, all right, the probability of getting a 5 or 6 is 1/3, regardless of what happens with the coin. They're independent events. They don't influence each other. Now, what we were talking about up here in regards to my golfing and it raining, that's not independent. If it rains, I'm probably not going to golf. Okay, so the occurrence of the rain, in essence, is associated with a change in the probability of the other occurring. Or in regards to these cards, all right, these are not independent events. All right, because if A occurs, the probability of B changes. B is dependent upon what happens in regards to A. So that's going to be a really important concept as we go throughout the year, is that what is independence and how do we prove it in probability. And so we've got really three main formulas. These two things here are really the same formula. That's our conditional probability formula, the probability of A given B. That is on your formula sheet. And so what this is saying is the probability that event A will occur given that B has already occurred. It's just equal to the probability of A and B, the intersection of the two, over the probability of the given. So the probability of A given B is the probability of both of those things occurring over the probability of the given. And that's what that is saying right there. That's just the notation. The probability of A given B is the probability of A and B over the probability of B. So we'll be using that a lot in this section. And then we have independence. Whenever you're asked to show whether or not two events are independent, you get a couple of options. You can show this, that the probability of A and B is just equal to the probability of A times the probability of B. And then also the other way is to show that probability of A given B is just the probability of A. You know, for instance, if I were to say, okay, the probability that I'm going to golf on Saturday, let's just say that is equal to 0.8. And let's say that event B is the probability that is going to, let's say, rain in London, England, let's say. Now, those two events are almost certainly independent. Because it rains and because this has occurred, all right, we'll call this event B. It has no influence on A. I don't care if it's raining in London as far as whether or not I golf. And so the probability of A, given that B has occurred, well, it's just 0.8. It's just equal to the probability of A. B has no influence on A. So the probability of A given B is just the probability of A. It's just like flipping a coin. If event A is, let's say, rolling a die, and event B is that. So event A is rolling a die and getting a 5 or a 6, and event B is flipping a coin and getting heads. All right, what's the probability of flipping a coin and getting heads, given that I've rolled a 6? Well, it's still 0.5. B has no influence on A. So that's one way of showing influence. And then if we took that concept and plugged it back into that formula, A given B, it would just be, and so we would end up in essence, with this independence formula. Okay, so those are the two ways you're so independent. Now, these two things you have to memorize. You have to know. They're not on your formula sheet. This one is. And so it's just like a lot of things. Look, these concepts are best understood by looking at a large number of contexts, by looking at a large number of examples, large number of problems. And if you do that, then you can get good at this stuff. And your book does a fantastic job of having a number of different problems and so I really encourage you to get into it and to attempt the problems and to look at the answers and to ask questions about it. And the people that do that in general become pretty good at this stuff. So the first scenario we have is a two-way table, which we've done several of these at this point. We've actually done problems like this before in regards to these things. And so the first thing you want to do with the two-way table is get the marginal distributions. But let's see what this context is. So in 1912, the luxury liner Titanic struck an iceberg and sank. Some passengers got off the ship on lifeboats, but many died. The table below summarizes who lived by class of travel, who lived and died by class of travel. Suppose we choose a customer at random, or choose a passenger at random. So I guess the gist of this context is, do you think there's a difference really between those who survived in the percent that survived in first class, second class, and third class? And so you could find the percents there. But anyway, the first thing we're going to do is come up with our marginal distributions. Whenever you see one of these tables, go ahead and find the column totals and the row totals. And so when you add these up, there's total of 442 that survived, and there's a total of 786 and 65 that died. And then the total in first class would be that plus that, so that's 319, assuming I haven't made a mistake here. And so the total in second class would be 261. The total in third class would be 627. And the total number of passengers here is 1,207. And so I think a lot of these problems are pretty intuitive, but in regards to conditional probabilities, the probability one thing given another. So given someone's in first class, what's the probability that he or she survived? These given problems, you only look at what you're given. So we're just given the people in first class, so that would be this row here. Only look at what you're given. Then you say to yourself, okay, if you're just given these 319 people, what's the probability they survived? Well, that would be 197 over 319. And so that is approximately equal to 0.61755. Okay, now, so about 62%. Make sure and show the fraction. That's considered showing your work right there. As a matter of fact, you don't have to put the decimal unless you're asked for it, but it's a good idea, I think, to show the decimal just so that you can sort of understand what's happening here, and you can sort of see, hey, about 62% of the people in first class survived. All right, so if someone, okay, the other thing is this. There's different ways of wording conditionals. I think the most popular way is to say, given one thing, what's the probability of the other? But it could be this. It could be, they could have said, if someone was in first class, what's the probability they survived? That's another way of saying given. Or it could say, suppose someone was in first class. What's the probability they survive? That's another, so getting practice at the different wordings in regards to conditionals is important. So this one says, if someone selected survive, what's the probability they were in third class? So now, what are we given? This is the given part. That's our condition. If they survived, you can only look at their survived people. Those are the only ones we care about here. And so, given it's one of those people, what's the probability of their third class? Well, there's 151 in third class. 151 over the 442. And that would be considered showing your work. And there you go. The good news about a lot of these probability problems is if you understand what you're doing, a lot of them are just sort of one-step things, just dividing two numbers. So there you go. Okay, then we have the concept of multiple events. Whenever it asks not just what one person, but in this case 3 people, when it's multiple events, you have to multiply your probabilities. And as we'll talk about a little bit later, the only way that you can multiply events is if you know they're independent or if you take into account their conditional nature. And I'll show you what I mean by that. You say to yourself, okay, there's 3 people. What's the probability that the first one, so it says, what's the probability all 3 died? Well, there's a total of 765 people that died out of 1,207. So the probability of selecting one person and they ended up dying, that would be 765 over 1,207. Then the conditional part of it is this. Given the first person you selected died, what's the probability the second person selected died? Well, you've taken one out, and so there's only 1,206 people left, and there's only 764 people that have died left. Okay, so you will multiply those. When you're looking for the probability of multiple events, you must multiply. All right, and so then, all right, given that the first 2 you selected has died, what's the probability the third one is selected died? Well, you've taken out 2 people, so there's only 1,204 people left, and you've taken out 2 of them that died, so there's only 763 people. And so you would multiply those 3 probabilities, and that would be 0.2542, right there, approximately. And there you go. And so showing your work is showing that multiplication. And do put your proportion here. Because I think it helps you see, in general, what's going on. So in this case, if you pick 3 people and they all ended up passing away on this thing, then it's not that unusual. But so anyway, so that's a two-way table problem. So then we've got this problem. Now this problem may sort of appear to be a Venn diagram problem, but it's going to be making use of our conditional formula. up here, our conditional formula. So, okay, so at a particular high school, 42% of students drive a car to school, 26% of students at the school are going to the homecoming dance, and 20% of the students both drive a car to school and are going to the homecoming dance. So we have overlap. And so this could very well be a Venn diagram problem, but on the conditional, we're just going to use the conditional formula. If you randomly select someone from the school, what's the probability they'll drive a car to school given that they are going to homecoming? So that's a conditional. And so you would use the conditional formula. So the notation for this, so I will say, let C represent driving a car to school, and then given they're going to homecoming, so I'll say let H be for homecoming. All right, and so our conditional formula said the probability of one thing given another. It's the probability of both of those things, driving a car and homecoming. In other words, the overlap, over the probability of what you're given, the probability of the second one, right there. And so in that case, for part A, so that is going to be, so the overlap is 0.2. That is the probability of both of them, so that would be 20% or 0.2. And then the probability of homecoming is going to be 0.26. All right, like that. And so that is equal to 0.7692. So there we go. So so that is, and that's considered showing your work, showing that division like that. All right. Okay, if you know someone drives a car to school, what's the probability they're going to homecoming? So what that is asking you, this is a given statement. That's a conditional statement. It's making a condition. If you know someone drives a car to school, so given they drive a car to school, what's the probability they're going to homecoming? So we use the conditional formula. It's the probability of both of those things, homecoming and drive a car to school, over the probability of the given. The probability of the second one, like that. And so that would be 0.2 over the probability of driving a car to school would be 0.42. And so that is equal to approximately 0.4762. It's a good idea to use at least 3 sig figs. And so there we go. And then the last part of this scenario is to show whether or not they are independent. Now, you have two options as far as mathematically showing independence, either of these two things. Okay, either of these two things. So we'll do the first one. If they're independent, then when you multiply their two probabilities, it will equal the probability of the overlap. It will equal the probability of the overlap. So in this case, what that means is the probability of driving a car to school and going to homecoming. If they're independent, they are independent if, and that would be equal to the probability of driving a car to school times the probability of homecoming. And so if that were the case, and so we don't, so the overlap is 0.2, the probability of driving a car to school is 0.42, and the probability of going to homecoming is going to be 0.26. And so this, in fact, is that equal? So 0.2, in fact, is not equal to, then that times that would be 0.1092. And so you could say, therefore, they are not independent. In other words, the occurrence of one is associated with a change in the probability of the other one. Now, and then the other way may actually be a little more intuitive. All right, so if they're independent, the probability of one given the other, let's say the probability that they are going to homecoming given they drive a car to school, if they're independent, then that's just going to equal to the probability of homecoming. If they're independent, it doesn't matter whether they drive a car to school, their probability of homecoming is not going to change, and that, in fact, is 0.26. So this is 0.26. But we just found in Part B the probability that driving a car to school or going to homecoming given driving a car to school is 0.4762. In other words, if someone drives their car to school, they now are more likely to go to homecoming, which maybe makes some sense. Those two things are not equal, so you would say, therefore, H and C are not independent. The occurrence of one is associated with a change in the probability of the other one. And the same things occur with the probability of car given homecoming. If they were independent, it'd be 42%, but it is actually about 77%. So that is that sort of problem using the formulas for conditionals. So Okay, then we have a popular sort of problem is a tree diagram problem. All right, very frequently, when you're given conditional probabilities, like these, you weren't given conditional probabilities, you were asked to find them. You were asked to find them. Very frequently, when you're given, okay, oftentimes, when you are given conditional probabilities, in other words, the probability of one thing given another, when you're given conditional probabilities, make a tree diagram. Make a tree diagram. Now, that's not the case every time, but it can really help, and there's a number of different there's a number of different questions that this could answer. Now, and some people like using the formulas for this, but I think to me the tree diagram is pretty intuitive. So, but I'll let you be the judge of that. But anyway, all right, so here's our next contest. So Sven has been invited to a Halloween party. There is a 70% chance that he'll actually go to the party. If he goes to the party, the probability he'll wear a costume on Halloween Day is 0.86. That is a conditional statement. It's saying if one thing's occurred, or given one thing's occurred, the probability that something else is going to happen is this. If he does not go to the Halloween party, the probability he'll wear a costume on Halloween Day is just 0.28. So if he goes to the party, he's probably going to wear a costume on that day. But if he doesn't go to the Halloween party, he's not going to wear a costume on Halloween Day. So these are conditionals, and so this is what we do. So the first event we have is whether he goes to the party or not. And so I'll call that event P. And so that is, there's a 70% chance of that. So I'll make a little tree diagram. So we'll let P, so P represents going to the party, is 0.7. And so that means, what is P complement? In other words, what's the probability he won't go to the party? Well, it would be 30%, just 1 minus that. All right, and then it says this, if he goes to the party, in other words, if he makes it to this part of the tree diagram, all right, the probability he'll wear a costume on Halloween Day, and I'll call that event C for wearing a costume, is 0.86. Well, then, what does that mean? It also means that if he goes to the party, the probability he won't wear a costume, C complement, would be 14%, or 1 minus that. All of our pairs of branches have to add up to 100%. So then it says if he does not go to the party, in other words, if he's at this part of the tree diagram, the probability that he is going to wear a costume is now 0.28, like that. And so that means if he does not go to the party, the probability he won't wear a costume is 1 minus that, and so that's going to be 0.72, like that. Now we can find the probability of each of these 4 pathways, in essence, which is what we could be asked about. So if he goes on the tree diagram, he goes to the party and wears a costume, what's the probability of that? What's the probability if he goes to the party and wears a costume? Goes here and that, this and that. Well, you multiply. And means multiply. Now, you can only multiply if you know events are independent, which they're certainly not here. All right? Or you take into account their conditional nature. And that's what the tree diagram is doing. We're taking into account the condition of going to the party. So that would just be, you just multiply the branches to get there. 0.7 times 0.86. And that's equal to 0.602. All right? Then, what about this route here? All right, what's the probability he goes to the party? This event is he goes to the party and he does not wear a costume. He goes to the party and, C complement, does not wear a costume. You multiply those, 0.7 times 0.14. And so that ends up being 0.098. And those two things add up to the branch they came from, 0.7. Then we have, if he doesn't go to the party. Well, this event is that he doesn't go to the party, but yet he does wear a costume. What's the probability that that's going to occur? Multiply the limbs to get there, 0.3 times 0.28. And so that, in fact, is equal to 0.084. And then lastly, the probability that he will not go to the party and he will not wear a costume. And so multiply the two limbs to get there, 0.3 times 0.72, and so that is equal to 0.216. All of these things, if you've done it correctly, should add up to 1, and that's a good way of checking to make sure your probabilities are right. Those two probabilities should add up to the limb that they came from, which they do, and so there we go. And so you could be asked about any of these. You could be given this scenario, and you could be asked, what's the probability Sven won't go to the party, but yet he'll wear a costume? You say, oh, that's this event. And so that's 0.08. Or you could be asked, what's the probability he'll go to the party and not wear a costume? And you say, oh, that's that event. You know, now some people like just using the formula for this, for conditional probabilities in essence, and they just calculate this without the tree diagram. But to me, the tree diagram, it just makes it easier to see. All right, so let's see what we're asked here. What's the probability he'll wear a costume? Well, there's two events where he actually wears a costume. That occurs here. That event there, he's wearing the costume there, and he's wearing a costume here. He's wearing a costume when he goes, this is the percent of the time he wears a costume when he goes to the party, and this is when he doesn't go to the party. In these two events, he's not wearing a costume. So we would just add those two up, and so this would be 0.602 plus 0.084, and so that is equal to 0.686. So there is a 68.6% chance that he will wear a costume on Halloween Day. And showing the tree diagram and showing that addition is considered showing your work. So make sure and don't ever put, naked answers, as we call them, without any sort of work shown. So this would give you essentially correct for that situation. Then it says, given that Sven wears a costume on Halloween Day, what's the probability he's going to the party? Well, so we have a conditional. Well, we'll have to use the conditional formula. So what is the probability, or our given? So given he's wearing a costume, what is the probability he's going to the Halloween parties? So that would be that. Now, in the problem up here, we were given a reversal of a condition. All right. In other words, we were given what's the probability he's wearing a costume given party. So this is a reversal, and this is an application of Bayes' theorem, which is somewhat of a complicated formula to it, but to me it's easier to do with a tree diagram. And so, well, let's use the formula for our conditional, which we learned on the other sheet, other side of this paper. And so the probability of one thing given another is the probability of both of those things, party and costume, over the probability of the given probability of costume. And so that we found up here, and so that would be 0.602. And then the probability of costume, we just found that in the part B here. So that's the probability of costume is what we found there. Probability of costume. And so that would be 0.686. Right? And so when you find those two things, it'll be 0.87755 approximately. So in other words, if he's wearing a costume, if we see Sven wearing a costume, there's about an 88% chance he's going to the party. Okay? So there we go. And then, so that's pretty much section 5.3. But a couple things. When can you multiply probabilities? In other words, you're given, you're asked to find the probability of multiple events. Like, what's the probability of getting, let's say 4 card, like let's say getting 4 spades or something like that. You can multiply. Number one, you can multiply when the events are independent. You can multiply them. Or 2, if you can multiply them if you have taken into account their conditional nature. Their conditional nature. And that's exactly what we have done up in this tree diagram. We've taken into account their conditional nature. Okay, thanks for watching and listening, and I hope you have much success in conditional probabilities, tree diagrams, and independence.